Hi guys, welcome back to this channel, Fitted Technologies. In today's video, I'm going to show you how to model a composite laminate at the scale of mesomechanics, or we can say a mesoscale modeling of composite materials. So in previous video, the one here that I show you in the screen, I already give you a tutorial on how to model a composite laminate using a macro scale modeling. In this case, we only have one single layer of continuum shell, but then this continuum shell is actually having several plies with different orientations. And in today's tutorial, now every ply is modeled explicitly. The difference is that in the tutorial today, we will be able to simulate the delaminations because now each ply are modeled explicitly. So if you are interested to see how the delaminations occurs, how the transverse cracking in affected the delaminations, you need to go to this scale, the mesoscale. At this scale, where the ply where the plies are modeled explicitly, this is the scale that you want to target, not the macro scale. But in terms of computational efficiency, of course, macro scale is better, right? It's cheaper in terms of computation. You can model a large size of part, yes, but if you want to go deeper, modeling the damage, for example, the transverse cracking, the delamination, this is something that you cannot do with the macro scale. You need to go down to the mesoscale, so you need to model every single ply, and each plies will be connected using the cohesive behavior or cohesive element. It really depends on how you want to do it. So let's go now. So in today's tutorial, we are going to model a cross-ply laminates. So what is a cross-ply laminate? So a cross-ply laminate is usually a kind of ply that contains 0 degree and several 90-degree n times, and you have also another 0 degree. The 0 degree can be m times. Usually the m's is smaller than n, so it means that usually you can have like 0 4 98 and 0 4. So it really depends on what you want to model. In this tutorial, we're going to make it simpler. We're going to use 0 90 90 and then 0. So we're going to have a two plies of 90-degree ply. Okay, so the property is shown here. So it's basically, I took it from publication. I forgot which one. It's a carbon epoxy, I think. It's a standard 45 GPa and all that stuff you can read from the literature. This data is usually resemble the carbon fiber data. All right, so all right guys, so let's continue again. We are going to model this composite laminate at the mesoscale using two different approach. So the way we tie one ply to another, uh, we will model it using cohesive behavior and cohesive elements, cohesive contact behavior or cohesive elements. So first we're going to use cohesive elements. It means what you need to do is basically to create a part. For example, one ply is 1 to 5 millimeter, so four plies is around 1 millimeter, right? Four plies, 4 millimeter, 1 millimeter. So what you need to do is to make 1 millimeter thickness, 1 millimeter, and then we are going to make a partition, for us to make to divide it into four separate regions. Okay, and the length will be around the standard 200 millimeter length, and the width will be around how much? 25 millimeter. Okay, so let's do it first by making part. I'm going to be fair fast here because I already make another videos other videos in my YouTube channel that tell you how to do it very slowly. So let's do it very quick. Make it 0, 0.0, 0, you can type it if you want, or you can click it. Now put it 200,25 and then click enter, and then you can just close it and then click done, and then you make it one depth, 1 millimeter depth. Okay, this is great. So now you want to make a partition. So we are going to make a partition by using create offset from principal plane. We're going to make a datum plane. Okay, a datum plane is it's like a construction plane that helps you to make a cutting. So it's just like a tools to help you. So now we are going to make a datum plane in the xy coordinate, in the xy plane. Now the first plane will be 0.25 offset, right? And then the second one will be 0.5, and then the third one will be 0.75. Okay, and then I want to make again the one for putting cohesive elements. So I want to make a cohesive element between the 0 ply and the 90, and also the 90 and the 0. So I want to make it 0.25 1. Okay, so I have a cohesive element with thickness 0.001, and the next one I want to make it 0.751. Okay, so to make you understand a little bit, what I'm doing just now is basically, imagine this is 1, so this is 0, so I'm making the first one here, the first cutting. This is 0.25, and this is maybe 0.5, right? This is 0.75, and then what I'm doing is I'm making another datum plane that is slightly higher, 0.251. So this guy has a thickness of 0.001, and also here I also have 0.001. But in the middle I didn't make it cohesive elements. Why? Because this is 90-degree and 90-degree, so it's impossible to have a delamination here. Delamination will only occurs between the 0 degree and the 90-degree here, or this guy. That's why I only put cohesive element in these two phase. Yeah, so delamination only happens when the orientation of plies are mismatched. All right, so one of the triggers why delamination happen is because there is a mismatch between the orientation of the plies. I hope it clear. Now let's make the partition, guys. Partition, defining cutting plane. We are just click and hold. Okay, left click and hold, and then choose this guy using datum plane. Now we're going to use the datum plane, the one below. Create. Okay, now we are going to choose the second one. Done. And then we are going to select the upper datum plane, and then we're going to choose this guy, and done. Then we're going to use this guy, and then choose this guy. Yeah, we choose the lower one, and then we're going to use this guy, but then we're choosing the upper one. Okay, so now you have a cohesive element here. Not yet cohesive element, we need to assign cohesive element, but here also. Great. So remember, in Abaqus the Hashin damage can be used for a continuum shell or conventional shell. When you're doing conventional shell, your geometry has to be a plate geometry. If you want to use continuum shell, your geometry should be a solid geometry like this. Even this is solid, but later the element is not a 3D solid element, but still a continuum shell element. So the kinematic is still two-dimensional, but the appearance is a solid 3D. Okay, but actually they don't have the solid kinematics. It's totally different with solid elements, even though you can see it like a three-dimensional solid, but they don't have this solid elements kinematics. Okay, so they are still working like a shell elements. Okay, so now what we are going to do is to get material here, mechanical elasticity. I'm going to use engineering constant, maybe. No, lamina is okay. I'm going to use this data here. Where is it? E1 4513 45,000. Is it thousand? Yes, 13,000 MPa. Huh? And new one two is what? 0.3 G12 6 4 500. This is 6,000. Make sure the unit. Oh no, this is usually 6,002. This is 4,500. You know how I know it? Because usually when you're modeling composite like this is the fiber, and this is the, so this is orientation 1, this is 2, and this is 3. The shear in this direction is usually the same with this direction. So 1 3 is usually the same like 1 2, but 2 3, this kind of shearing. Yeah, so 2 and 3. Okay, this is 2, this is 3. So this kind of shearing, yeah, they are different. So they're usually more softer because you just working on the matrix. That's why usually the value of the G23 is lower than G12 or G13. Okay, so now it's done. We are using lamina, and then if you want to use the damage for the composite, you can use Hashin damage. Use longitudinal strength. We have the data here, I think 1600. Yes, I said before it's 1000 and it's 600. Usually the compression is lower, so it's easier to make a fiber kinking during compression rather than doing a fiber breakage during tensile. So it's more difficult to break the fiber. It's easier to make the fiber kink or buckling. And this one, transverse tensile, the value is 40. The same, but it's different here. When you're compressing the matrix, usually the strength will be like 3 times, and then it's 60 60 60 60. Okay, this is the strength, the maximum stress that you can reach before you initiate damage. Now is this damage evolution. You need to put this fracture energy. I will just be quick. It's the type energy. You have 9500 0.4 0.4 9500 0.4 0.4. Okay, okay. And then in terms of stabilization, you can put a small value. I recommend 10 to the minus 4, but for the sake of this tutorial, I'm going to make it 0.001 10 to the minus 3 to make the simulation faster. But of course, you a little bit compromise the accuracy. If you want higher accuracy, make use smaller of it. 10 to the minus 4 will be good recommended values, but I will not do it right now. Okay, clear. So now what you need to do is to use shell and homogeneous, right? Because it's a shell. Okay, so the thickness is, what is the shell thickness of this guy? I forgot. The thickness is 0.25, right? Each of them. And then they are okay. And then assign section. This guy. Oh, you need to assign to everything, right? Yeah, to everything. Yeah, section. So now it means they have the same material. The only difference that they have a different orientations. All right, they have a different orientations. So you want to give, where is it? You want to give different orientation to this guy. The way you do it, you can use from here or either here. In Mesoscale, I prefer to do it here so I can assign for different region one by one. Assign material orientation. Okay, and then select use default orientation. I really like to use this coordinate system, this one. And then my axis is x3 axis, and then this is rotation 0. All right, and this one the same thing. I like to use the coordinate system is 0. Now this guy is 90, huh? See, so it's rotate. If I make it 45, look this guy, the number one is the fiber directions. So 0 mean like this is the fiber, and then 45 means this, the fiber is in the 45 degree, but now I want to use 90. Okay, and then the same here, I'm going to use the 90 also. Okay, 90, and then here I'm going to use global coordinate system. This is, I'm going to use 0. Okay, done. So now they have different properties. So cross-ply, I'm going to save it first just to make sure it will not crash at one point. And then I'll okay, click OK, nothing changed here. Just tab, and then to create tab, static general. You can turn it on, but this is very low strength, lower than 5%. I don't care about the high nonlinearity of the geometry, but I do need the stabilizations, and then I needed to make it smaller, and I will initiate with very small time increment, and then I will allow a larger number of increment. And then as usual, I'm going to set several iteration parameters. For example, here I'm going to allow the cutback times around 20 times. So the idea is that when Abaqus try to solve something, they choose an increment, time increment, for example 1 second, and then they try to solve for this 1 second. If it doesn't converge for 1 second, they will cut the time step 4 times, so it's become 0.25. They try to solve 0.25. If it fails, they cut back again 4 times, so it's become how much? 0.05 something something. So if they cut 5 times and still it didn't work, Abacus will tell you that okay, guy, it's error. I already make 5 times, but it's not enough. So the default value of this IA is 5 times. But because our simulation contain damage, sometimes it is difficult to get a convergence. So you need to allow for more cutbacks. So 20 cutbacks. This is setting for iteration to tell your Abacus when to give up. Initial value was 4 and 8, but that's too low. Now I increase the number to 20 and 40. Okay, and this is step. This is very typical. If you see my video, I always use evenly spaced, and make sure you choose this Hashin thing so you get the output for the Hashin, and also SDG because you're going to use the damage. Oh, okay. Okay, this is the Hashin. Okay, and then I'm going to, where is it? Status, if I want. Oh, blah, 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 maybe I'm not sure what is that. I just click it. Okay, click OK. History output. If you want to see the energy evolution, where the energy has been absorbed, I can do it like this. 100. Okay. uh, I forgot something. I forgot to assign the material for the cohesive element, but let's do it first for the load. Okay, so now let's make this guy a fixed boundary. Okay, so in order to choose all of them, just choose face here, and then there will be a face angle here. You can choose them at one time, then click done, and then you make everything fixed. Okay, same thing here. You want to click here, click displacement rotation by face angle, click done. You want to check everything, but this now you want to make a X. Okay, the X direction you pull, the total length is 200. If you want to apply 5%, it means you need to apply for 10, but I want to just apply for 22.5% maybe. So we'll just make it 5 or maybe 7. 7 is around 3% strain. That's more than enough. Yeah, so I pull 3% or 7 millimeters from the total length of 200 millimeters. So now uh, let's come back to the property before we mesh. I think I already assigned. So if you want to see if you assign material or not, click here, property default in materials. So the color is changed. It means that you already assigned a property. Oh, oh, did I choose that? Mm, create another material, mechanical, elasticity. For the cohesive elements, you want to use distraction. This is a large number usually because you want to model a delamination. So it's actually a near zero thickness cohesive element to model the correct the delamination. So this is not a real material property, but this is more like a numerical parameters to make sure the continuity of the stress field in the boundary. So you need to use this value big enough, but not that big so that it will cause a convergence problem. Okay, and then here mechanical elasticity, and then you want traction separation, quads S, and then nominal stress you want to use, say, I don't know, how do you want, 40 and 60, 60, yeah. And then for the damage evolutions, energy, and then you want to make sure you're using BK maybe with power 1.2, and normal fracture energy is mode 1 is 0.4, it's 1.2, 1.2. Okay, so how to get this energy detail? If you ask me, from the experiment, you need to do DCB experiment for the normal mode 1. For the shear, you can do a ENF, and notch flexural beam test. Yes, ENF beam test. Okay, and then you can do the ENF for different kind of mode mixity to get this power. So yeah, read the HTM standard. Okay, and then the same thing here, stabilization 0.01, recommended value 10 to minus 4. Okay, click. Okay, now I want to use others, cohesive, material 2, traction separation. Yes, and then for the first cohesive, done. Section 2. Okay, for this guy, section 2. Okay, so now it's good. The middle you don't have cohesive element because it's between 90 and 90. Okay, now you do the mesh. So create mesh. I always recommend it for this coupon task. You always use 1 millimeter. That's the recommended size for me. Yeah, it's nice, right? And this day computational tools like your laptop is very good, quad core, 8 core, so you don't need to worry about that. And to make sure the stacking sequence is correct, you can click tools query and make sure the mesh stack orientation is correct, especially for the cohesive element. This one is okay. I'm not sure about this one. Yeah, okay. There's inconsistent, he say, so it's better to make it good, just like this. And then you choose everything, and then select the top face as a reference. So I just choose this guy, the top one. And then yes, done. So if you see here, they are very good now. This is the top face, this is the bottom face, and it means that everything are well oriented. The cohesive element are good. Okay, and then let's assign a type of element here. Assign element type for this guy, this guy, this guy, and this guy. Click done. There are 3D stress. You're using second order, accuracy, enhance hourglass. Make sure that hourglass is not there. Element deletion, yes. Just to specify in 0.999 to make sure that you don't have division by 0. If your damage equals to 1, it will cause problems sometimes, because at one point you may divide something with 0, because when the damage equals to 1, it means the stiffness will equal to 0, and it's not good. It's not good. You may have problems later on. Okay, and now we want to assign for the cohesive element. This is the first one you click, and then you click for the second one. Okay, so you click only those two parts, click done. Then make sure you're using cohesive. Viscosity now 0.01, same. Recommended is 10 to the 4, okay? 0.999. Okay, just to make sure you don't have division by 0. Click done, and okay, now you can run actually. I hope we can run it. Let's see, because I already assigned everything. L cross-ply. We're going to have a, this one is using cohesive element to how to say, to join the ply. Later we're going to have another one by using cohesive contact behavior. I'm going to use 2, and then click here and submit, and I hope it's running. Let's see, let monitor is processing right now. It's submitted and it's running, hopefully. uh, yeah, it's running now. Let's see. Oh, it's error, guys. There is two 20,000 element meshing properties. The element C, it's nice that you have this error. So next time when you do it by yourself and then you found this error, you know how to check it. So if if you have this error, you want to see which element has missing properties, right? So you go to results, you go to the results, and then you click output database cohesive. So then there's element set here, and then there's this guy, element missing. Error missing section. It seems that there's a missing section in incorrect properties. Yeah. Oh no. Yes. We were using 3D solid for the for this guy. No, no, we should not. So here, before I choose this guy, I choose this guy, I choose this guy, I choose this guy, I click done, and then I use 3D stress like this. Okay, this is wrong. You want to use continuum shell. Okay, this is shell formulation. Viscosity the same, 0.01. And then you want to use enhance hourglass control, element deletion, yes, maximum degradation 0.999 to divide, to avoid division by 0. Okay, and then click OK and click done. See, then you go again to job, and then you submit again, and then okay, It's nice that we have aborted the the job, because it enforces us to think again what caused the problem. Now I realize that we assign a wrong element type, because here in these properties we make it before using shell and homogeneous, right? But then the element formulation using the solid before, and that's why it goes error. Now we fix it, now it's running without any problem, hopefully. Yeah, just some warning, for example. Yeah, but you don't need to care about this. Yeah, it's running now. It start calculating, so I will resume the video when it's done. Hopefully it goes well without error. Okay. All right, guys, welcome back to the videos about this modeling of this composite laminate at mesoscale. We are modeling it using the uh, uh, cohesive elements right now. So each ply are connected using the cohesive elements, like this one, to be to facilitate these delamination between the plies with different orientations. So it's still running actually. My computer is quite not really good computer. Only has two processor, for thread. Yeah, so it's quite slow. So, but now it's already like 20% of the total, 25% of the total time that we assign to the problem. The total time is around one. Now it's already 0.26%. So we apply around 3% total strain. So we put it up to 3%. So now it's already finished the quarter of it. It means that now it already reached 0.75. And if I'm not mistaken, the 90-degree usually fail around 0.3 to 0.4%. So it means that if we see right now, even if the simulation hasn't finished, there should be some kind of matrix damage due to the tensile loading in the 90-degree ply. So we can check right now. Yeah. All right. Let's check. Yeah. Yeah. This one is due to the cohesive element. The upper part and the lower part, you see the color is blue. Now it's damaged fiber tension. There's no fiber tension because I calculate before this. Uh, we input the value around how much, 1000 MPa, and the stiffness is around 45,000 MPa. So it means that it will fracture at this strain, 0.0222 or 2.2% strain. So it's almost 80% of the strain that we apply 3% right now. So that's why there's no fiber tension damage right now. But if we see, let's hide these zero plies uh using this. I think, yeah, this is the cohesive ice. Why it's gone. Oh, let's and then let's hide it again. We're going to hide based on section, because they have different section. This is the cohesive now. We're going to, why. uh, it's so difficult. Yeah, so if we choose matrix tension, you can see, oh my god, what happened to my laptop? My laptop is not that good one. uh, oh, it's really disgusting, guys. Uh, I cannot choose this guy. I don't know why. Let's come back again. Job, result again. Let's play animation if you want. So the white one is the cohesive elements. right now. So I think if you set SDEG, there's no damage yet so far. Let's remove it. Remove selected. This section. Yeah. We'll remove this section. We'll remove this section. So now it's basically showing us two layers of cohesive elements. The one in the top 090 and the bottom 90 0. So everything now, oh yeah, at some point, maybe usually near the boundary, SDEG start to occurs, but I don't know where. Usually near the boundary, yeah, I'm not sure where, but there's here. Yeah, I don't know. So there's no damage here. So now let's invert the display. Yeah, and if we see matrix tension, you see it's many regions already damaged. Here the interior part are damaged due to the due to the tensile loading. Now we are still around 0.5%. Quarter of the loading, the core loading is 3, so the quarter is 0.7. That's why many places already damaged in the 90. I want to show you again. Wait, remove selected here. Done. So here, yeah, damage happens everywhere. There's many transverse crack. Yeah, it makes sense now. Something like this happens because we are exceeding the strain that is required to initiate the transverse crack, and now all this region has the same threshold of transverse cracking, that is 40 MPa. If we see this, where is it? The the how you call it? The maximum stress for the transverse tension. I put the 40, I think 40 MPa, right? So when these elements reaching 40 MPa in the transverse direction, sigma 22 reaching 40 MPa, it means that all these elements are experiencing damage. So their stiffness will be degraded due to this damage. But the fiber itself, up to now, they're not yet damaged, because to make it damage, you need a 2.2% applied strain, while the simulation now still reaching 30% of 3%, so it's 0.9, so it's still far from damage. But I think if you wait enough, yeah, it will damage later. Okay, so I will stop here, guys. I'm going to show you the result in the next video, and in the next video I will also discuss about the modeling of the same problem but using cohesive contact behavior, instead of using the cohesive elements. Do it with elements. Now we did it now. We did it already with the cohesive elements. Now we are going to do with the cohesive contact behavior, and I'm going to show you in the next section how in the next videos how we are going to do that. Okay, see you again in the next video, guys. I will stop now, and let's see the next part.